Good day, sir. We are Group 8 and this is our title, Ground Up Developments of Keyword Spotting Using CMSIS Library CNN and Short-Time FFT. So our teammate have Prasan, Weifang, and me, Weizin. As we know that communication is very important in our community, but in the deaf community, communication is having difficulty, especially during an emergency situation. So this system is mainly implemented to help to break the boundary of communication between normal hearing community and also the deaf community, which is the LED replace voices. So this system will translate out the speaking into LED blinking. For example, when we speak one, the LED will blink once, and if we speak two, the LED will blink twice. The objective of our project is to design a voice to LED blinking converter using CMSIS NN and CMSIS DSP FFT functions with debugging input from the ground up, and also to ensure the design able to work with the CMSIS libraries. From here, we can see the overview of our projects, which we separate into the two main flow, which is a training flow and also execution flow. And it's go through the process of 2D arrays time slice, then undergo the FFT algorithm, then 2D array frequency bin slice, and then we feed the data into a CNN training intensive flow, and then we make the training and training flow and the execution flow to work together and do the classification into classes. Next, we will go to the methodology. Weifang, please.
Yeah, so I will start on methodology. We convert the wave audio sample through the microphone into 1024 sample window for each sample at 8000 Hz sampling rate, which give approximately 0.128 seconds of audio. And then repackage this linear array into a 32 by 32 2D metric image. After that, do an FFT transform on each row of 33 to obtain the frequency bin of each 4 milliseconds of audio. Next. Yeah, so this is a type of wave we collect and show in image form 32 times 32 times by frequency metric for audio in Python matplotlib. Next. We did the training with TensorFlow 2.0 with the CSV 2D frequency bin image in training machine. From here, show the CNN architecture of 2D convolution, 2D polling, again 2D convolution, 2D pooling, 2D convolution, flatten, dense, and dense. So construct a desired convolution neural network architecture. This result in a CNN architecture with the following parameters and outputs. This training result in the CNN having the following train weights and biases. Next. After that, using a custom C program algorithm to quantize the double types linearized array and generate this quantized linear array in C header file in training machine. So from here, we can see that using this simple algorithm to quantize the linear double array data into a integer 8 Q1.7 fixed point numbers. Finally, put these two quantization function and header file generation function together to generate the header file containing the linearized Q1.7 fixed point array that can be directly included in the ARM-Qs or STM32 cubes ID. So I will pass the rest to Prasan.
Okay, just like in the training machine, in our inference machine, we also have three major components. So the first major component is the I2S part, which reads from the microphone. So first we read the data from the microphone via the I2S interface, which writes into anti-buffer and sends debugging messages to the host computer's PuTTY terminal via the previously configured UARTX DMA. So as you can see in the second picture, we are showing you an example of the resulting debugging message that is viewed from a host PC via PuTTY terminal, which is sent from the STM32 microcontroller. Next slide. So the next important part is also the FFT algorithm. So first we create an FFT instance and configure the size and so forth, which we then pass into the FFT function, which also takes in the pointer to the input buffer and output buffer. And this, once it has all the information, the FFT function can perform the FFT operation. Okay, next. The next part is the CNN part of the inference machine. So to implement the sequential neural network architecture on the inference end, several CMSIS library functions that make up the convolution, pooling, and densely connected neural network layers need to be used. These functions perform the same operation as the TensorFlow counterparts. So first here you can see we are including all the weights and biases into the C code of the inference machine. And in the second picture here, we are showing you the waterfalling, the sequential nature of the neural network architecture reconstructed from the training machine as seen in the second picture here, which passed down from layer convolution, pooling, convolution, and dense layer finally at the end. Okay, next. So in order to know what this dense neural function does is that the dense layer, which is one of the layers that we are using here, can be viewed as a densely connected graph of interconnected nodes via weighted edges, while the computation of the densely connected neural network nodes and weighted edges are realized using matrix and vector multiplication that is passed onto an activation function for each nodes. Okay, next. Next layer we use is also the pooling layer, which resizes the image. The pooling function used here is the max pooling function. This pooling function finds the maximum value in a region of the image matrix and picks out the smallest value, essentially resizing the image. And the other layer type that is used is the convolution function. This convolution function uses a sliding window called the kernel, which slides across the matrix image that performs a convolution operation on the image, resulting in a resized image with features that are present in the image enhanced. This is because the effect of sliding the kernel across the image picks out the presence of the image a feature in the detected feature in the image. Each layer of the convolution builds upon the feature that was detected on the convolution layer preceding it, causing the resultant image from multiple sequential functions to reveal more complex features in the source image. Okay, next.
Okay. So here's the result of our project. You can see this is the PuTTY terminal, and the final code running on the microcontroller will debugging to the PuTTY enable. Okay, and this is the tabulated data by comparing the spoken and the CNN detection result. So we can see the accuracy is actually at 30%. So in conclusion, the development of the keyword detection CNN using TensorFlow and ARM CMSIS from ground up is demonstrated successfully. And future enhancement is needed to ease the acquisition portions of the training, as the bottleneck of this project is the amount of training data available. Okay, here Prasan will show the demonstrations of the system.
Okay, here we can see the code running now. You can see if I say 1, it will bring once. If I say 2, it will bring twice. And if it will blink twice with the frequency of the first, it blink twice at the frequency of the 1. Okay, and that is all from me. Two, 1.
Okay, that's all from our team. Thank you, sir.
Thank
Bye-bye.
you.